Let us see the pulse parameters measurement using a CRO. So, we have seen the various applications of a CRO. That is, we can use a CRO for measurement of voltage, for measurement of current. We can measure the phase difference. We can measure the depth of modulation. We can measure the current. We can also use the CRO to measure the pulse parameters. We can measure the phase difference of two signals. Next, we can see the composite synchronized TV signal. We can also measure the radio frequency, intermediate frequency and audio frequencies in radios and TVs. We can also see the radiation pattern of an antenna. These are the various applications of a CRO. So to start with, we can measure the amplitude of a sine wave, or we can find out the amplitude of any waveform. We can measure AC voltage, we can measure DC voltage, we can measure the frequency time period also. So to start with, to measure the voltage with the help of a CRO, we usually measure the peak to peak value. The RMS value of the voltage can be easily calculated once we know the peak to peak value. To measure the voltage from the CRO display, we should observe the setting of the vertical attenuator, that is volts per division control, and the peak to peak deflection of the beam, that is the number of vertical divisions. So the amplitude of the waveform, that is voltage peak to peak, can be given as volts per division into number of vertical divisions. This gives us the amplitude of the waveform. So next, current measurement. The CRO is basically voltage indicating device. The current to be measured is passed through a resistor. The voltage across this resistor is applied to the CRO and the voltage is measured. This measured voltage divided by the known resistance value gives the unknown current value. To find out the time period and frequency of a waveform using a CRO, the time period is given as number of horizontal divisions for one complete cycle of the waveform into the time per division control. This gives us the time period of the waveform. Frequency is calculated as F equals to 1 by T. So this is how we can measure the voltage, the current, the time period and frequency of a waveform. To calculate the DC voltage, we have to calculate that as first you have to put the switch, AC-DC ground switch in the position of ground. Adjust the trace to be in the center of the CRO screen. Then you put the switch in DC position. Apply the voltage to be measured. The reference line moves up or down. If it moves up, it means the applied voltage is positive. If the reference line moves down, it means the applied voltage is negative. So number of vertical divisions shifted by the reference line into volts per division gives us the DC voltage of the applied signal. We can also measure the frequency and phase of a signal by using the Lissajous pattern. Lissajous patterns are nothing but when we have two signals, one known signal and one unknown signal, the CRO is put in XY mode, that is internally the sweep is cut off. Now the two signals are applied. When they are equal or multiples of each other, we get different types of patterns called as Lissajous patterns. Depending upon which pattern is displayed, we can find out the unknown frequency and phase of the signal. That is one more procedure. To find out the phase measurement using a CRO, as I told you, using the Lissajous pattern, you can measure, or if you apply two waveforms at a time, then the difference between a similar point on the two waveforms gives the phase difference of the two signals. Next, the depth of modulation of a signal can also be measured. It can be calculated as, the depth of modulation can be calculated as Vmax minus Vmin by Vmax plus Vmin into 100 gives you the percentage of modulation index. So this is how we can measure the AC voltage, DC voltage, current, time period, frequency, depth of modulation and phase of signals. Next, let us see how to measure the pulse parameters. So before knowing how to measure the pulse parameters, we have to know what actually the parameters are there in the pulse. So you can see in this figure, we have the rise time, the fall time, the sag or droop, the overshoot, the width of the pulse, the amplitude of the pulse, so on. So here you can observe the rise time. From 10% of the amplitude to 90% of the amplitude is first measured. The difference between these two is nothing but the rise time. Similarly, the fall time is nothing but the pulse amplitude falling from 90% of the maximum value to 10% of the maximum value. The difference between these two time periods is nothing but the fall time. Next, the width of the pulse is nothing but you have to find out the width of the or the number of horizontal divisions into time per division when the amplitude of the pulse is 50% of the maximum amplitude. So from this figure, you can see the rise time, the fall time, the width of the pulse, the amplitude of the pulse. Also, T equals 1/8. You can also find out the time period or frequency of the pulse waveform. So, a pulse waveform or pulse train is a type of non-sinusoidal waveform that is similar to the square waveform in which the voltage or current changes with time. So rise time. The rise time is nothing but the time the pulse takes to rise from 10% to 90% of its amplitude is called the rise time. So here you can see the rise time indicates how quickly a circuit responds. The rise time is the time it takes for a waveform to go from 10% of the normal amplitude to 90% of the normal amplitude. So this you can see, this is the rise time. So if you want to observe the rise time fall time of a pulse, you have to use a CRO with a big bandwidth specification so that you can easily observe the rise time and fall time. So here you can see the rise time is nothing but the time taken by the pulse to rise from 10% of the amplitude to 90% of the amplitude, that is the rise time. Fall time, the time the pulse takes to fall from 90% to 10% of its amplitude is called fall time. So already in the figure we have seen what the fault time is. So apply this pulse to it. CRO, find the maximum amplitude. Then on the waveform, pulse waveform, you mark where the 90% of the amplitude is. Then you mark or calculate where the 10% of amplitude is. Next, note down the time at which the 90% amplitude is achieved. Next, you note down when the pulse waveform has attained 10% of the amplitude. The difference between these two is nothing but the fall time. So you can see here the waveform falling from 90% of the amplitude to 10% of the amplitude. This is the fall time. Next is the pulse width. The time that elapses between the 50% level points is called as the pulse width, or the width of the pulse that elapses between the 50% level of its amplitude is called the pulse width. So you can see here it is indicated as the width of the pulse from 50% of the amplitude on both sides of the pulse, that is from left side on and on the right side, that is the rising edge, and on the falling edge you mark 50% of the amplitude, and the time period between these 50% amplitudes is nothing but the pulse width. So this is how you can calculate the rise time, the fall time, and the width of the pulse. So not only this, you can also find out the duty cycle, which is defined as the ratio of pulse on time to total time. Total time is nothing but on time plus off time. So using this, you can find out the duty cycle. Next, pulse repetition rate, number of pulses per second, is called as the pulse repetition rate or the frequency, as already we have seen in the figure. T equals to 1 by rate, that gives you the pulse repetition rate. So here the procedure, as I already told you, for measuring pulse parameters is, when we are measuring pulses, it is generally desirable to use the pulse source as an external trigger. The essential parameters of a pulse are the amplitude, the rise time, the fall time, the pulse width, duty cycle, delay time, and the pulse repetition rate. So the input waveform has steep leading and lagging edges, while the output waveform has measurable rise and measurable fall time. If the upper wave is the input to a circuit and lower is an output, a delay time might be measured. That is, a waveform with steep leading and lagging edges, and a practical pulse waveform, that is, which has the rise time and fall time. So if you give a waveform at the input with steep rise and fall times, and if the output is a pulse with rise time and fall time, noticeable rise time and fall time, then there will be a delay time which has to be measured. So rise time is the time required for the leading edge of the pulse to go from 10% to 90% of the pulse amplitude. Similarly, the fall time is the time taken for the trailing or the lagging edge to fall from 90% to 10% of the pulse amplitude. So the delay time is the time elapsed from commencement of the input pulse until the output pulse reaches 10% of the pulse amplitude. So the delay time must be less. The input and output should follow the input, and as soon as the input changes, output also should follow the changes immediately. Now, let us see the probes. So, different probes and connectors used in CRO. So, how we connect a circuit and a test to a testing or measuring device. Now, here our measuring device is a CRO. How will I connect the circuit to this measuring device? We can connect using a cable connector probe. So the oscilloscope probe should match the oscilloscope to the device under test, which allows the signal to be brought to the oscilloscope for a good display. Probes actually become part of the circuit, introducing resistive, capacitive, and inductive loadings. So for accurate results, the probe should be selected in such a manner that it has minimum loading effect on the device test. Oscilloscope probes form tuned circuits. They bring the signal of interest to the instrument. Basically consists of three parts: the probe head, the coaxial cable, and the probe termination. So there are different types of probes: direct probe, passive probe, active probe using FET, the current probe, the high voltage probes, etc. So direct probe, which is nothing more than a cable with a probe tip and no other components. It uses a shielded coaxial cable. Next, a passive voltage probe or a high impedance probe. It is a 10:1 attenuator. Oscilloscopes are typically used with a 10:1 probe. Active probe. One useful probe is active probe, which achieves a lower capacitance without the attenuation associated with 10:1 probe. Active probes are designed to provide an efficient method of coupling high frequency, fast resistance signals to the CRO input. So the active devices used may be FET, BJT, etc. These are useful for small signal measurements. Next is the current probe, very valuable probe. You need not disconnect the circuit through which the current is to be measured. Just you can clip it so that you can measure the current to the circuit. Isolation probe, it is also one-to-one probe. It is used in order to avoid undesirable loading effects of the shielded probe. Next is the high voltage probe, also known as voltage multiplier probe, which can apply voltage order of kilovolts to CRO. It is essentially a potential divider. The voltage to be measured is usually divided by a factor of 1000. So this probe head and probe tip, well insulated plastic or thermoplastic material is used to protect user from shock. So the parts of a simple probe which we use in the labs is it has a probe head, that is signal sensing circuitry. Next is a coaxial cable which couples the probe head to the termination circuitry, that is can connect it to the CRO, and termination circuit impedance matching to the CRO. So these are the three parts. You have the probe head, you have the coaxial cable, you have the termination. The probe head is connected to the device under test. Termination is connected to the CRO. So as I told you, typical probes are active probe, passive probe, high voltage probe, current probe, isolation probe, etc. So the most popular passive voltage probes, there are no active components, no attenuation, 1:1 probe. Just to touch at the point where the parameter has to be measured, it gives the reading on the CRO. So non-attenuating. A 50 ohms coaxial cable which gives approximately 30 picofarads per feet. So 5 feet cable means 150 picofarads to the CRO. Next, passive probe has large shunting capacitance. So these are normally used in low frequency applications. So passive voltage probe, mostly used probes are the passive voltage probes. We also have 10:1 probe or low capacitance probe. This is the passive voltage probe which has the probe and the CRO part. Now the probe tip or the probe head has 9 mega ohms in shunt with a capacitor C1 13 to 17 picofarads through a coaxial cable given to the CRO, so that this 9 mega ohms in the probe head has very good it avoids the loading effect of the CRO, so that we get the accurate readings. This is a simple one. The probe tip, the probe head, the coaxial cable, CRO. Next is the active high voltage probe. So used for coupling high voltage and fast rise time, which has high input impedance and less attenuation. This is the active voltage probe. It contains elements like FET diode and transistor. It is bulky and expensive. It uses source follower FET in the probe head. Probe termination is by active devices with 50 ohm impedance. So this is an active voltage probe. Here you can see a transistor, a coaxial cable to the probe tip and to the CRO. So this is used to connect. This is a high voltage probe used to connect kilovolt signals to the conventional CRO. So probe head has high impact thermoplastic material, has special protection from shock hazards. You see the probe. So you have a probe head, your coaxial cable, and the termination next connecting to the CRO. So current probe, as I already told you, provides inductive coupling. The various types, most widely used current probe is split core type. That is, you need not disconnect the circuit. It can be just clipped around the conductor whose current is to be measured. You can see here. Here you can see that you need not disconnect the circuit, just clip it around the path at which you want to measure the current. So this is the current. So here you can see you have a probe head with movable piece, so that movable piece is moved, and this is just connected across the wire or the conductor through which the current has to be measured. Next, this current carrying conductor on the transformer is connected to the coaxial cable and next to the termination. So this is the current probe. So this is a probe with red and black crocodile clips connected at one end and PNC connected at the other end. This one is mostly used in the laboratories for conducting the practice. So these are the different types of tips. Depending upon the application and the requirement, we'll be using different types of tips of the probes. These are the probe holders. So here we have seen